High above the plane of its host galaxy, two stellar remnants circle one another in an elegant yet volatile pas de deux. One partner is a neutron star, a city-sized sphere of nuclear matter spinning dozens of times per second. The other is a white dwarf, Earth-sized ember of carbon and oxygen, the final grave of a sun-like star. Together, they form a binary whose graceful orbit belies the enormous energies they exchange with every revolution. Born separately, one from a supernova, the other from the gentle shedding of a red giant's envelope, these remnants found each other through chance and gravity. Over millions of years, gravitational radiation bled their orbit of energy, drawing them ever closer. Now they whirl around a common center of mass, only a few 100,000 kilometers apart, closer than the distance between Earth and the Moon, with each orbit lasting mere minutes. The neutron star's immense gravity tides the white dwarf, raising bulges on its surface. The white dwarf, in turn, distorts the neutron star's magnetic field, modulating its beam of radiation like a conductor, prompting new crescendos in the pulsar's timing. As the pair draw even closer, the white dwarf fills its Roche-Lobie's gravitational safe zone. Material begins to stream from its surface onto the neutron star via an accretion bridge. This steady spill of hydrogen-rich gas forms a swirling disk around the neutron star, heated to millions of degrees by friction. Here, X-rays blaze. Every gram of matter spiraling inward liberates 1,000 times more energy than burning it in nuclear fusion. Observers detect X-ray bursts when enough material piles up on the neutron star's surface to ignite thermonuclear flashes. Brief, brilliant eruptions that last seconds but outshine entire galaxies in that moment. Despite these violent flares, the system's heartbeat remains the neutron star's rotation. Its magnetic poles channel infalling plasma into hotspots. As it spins, we detect pulses of X-rays and radio waves, a cosmic metronome ticking every few milliseconds. But those pulses wobble. The white dwarf's gravity tugs at the neutron star, causing slight Doppler shifts in pulse timing. By tracking these shifts, astronomers map the orbit in exquisite detail, measuring masses, inclinations, and even testing general relativity as the neutron star's strong gravity warps space-time around its companion. Meanwhile, deep beneath the electromagnetic spectacle, the binary emits gravitational waves. These ripples in space-time carry away energy, tightening the orbit further. With every pass, the frequency of the waves climbs, the orbit decays, and the dance grows ever more frenzied. Spaceborne detectors' future missions designed to catch low-frequency waves will one day eavesdrop on such binaries, hearing their inspiral long before the final act. For now, we infer their existence from timing and theory, anticipating the crescendo. As the orbit shrinks to tens of kilometers, tidal forces on the white dwarf skyrocket. It loses mass catastrophically, potentially leading to one of two climaxes. Accretion-induced collapse, where the white dwarf's core exceeds the Chandrasekhar limit and collapses into a neutron star, leaving behind a double neutron star binary. Thermonuclear detonation, where runaway fusion in the white dwarf triggers a Type Ia supernova, obliterating it entirely and briefly outshining its host galaxy. Either outcome marks the end of the binary's long duet. But for now, their harmony continues. Pulses and bursts, tides and waves, energy and gravity intertwined in a cosmic ballet. Deep within a red giant's core star bloated to hundreds of times its original Syzia, dramatic transformation is about to unfold. This is a star of roughly 2 solar masses, old enough that hydrogen fusion in its shell has exhausted the central hydrogen, leaving behind a dense, degenerate core of helium ash. Pressure mounts, temperature soars, and soon the star will experience a helium flash, a runaway ignition that reshapes its very heart in seconds. As hydrogen shell burning continues, helium ash accumulates in the core. Gravity compresses this helium until electron degeneracy, pressure quantum stiffness of electrons alone supports it. Degenerate matter behaves oddly. Raising temperature does not expand it, so heat cannot regulate itself. Instead, the core grows hotter and hotter, inching toward the critical 100 million Kelvin needed to ignite helium. From the outside, the red giant appears serene, its luminosity and radius nearly constant. But beneath the convective envelope, the degenerate core is a pressure cooker counting down to catastrophe. At some point, a small region at the core's center breaches the ignition threshold. Helium fusion begins via the triple alpha process, where 3 helium nuclei combine to form carbon. But in degenerate conditions, the energy released does not cause the core to expand and cool. Instead, temperature spikes further, accelerating fusion in a runaway chain reaction. In mere seconds, the core's luminosity soars by a factor of 10 billion, yet this energy is buried within and does not reach the surface immediately. The helium flash releases as much energy as the sun emits in 100 million years, but nearly all of it goes into lifting the degeneracy. The helium flash's heat finally breaks electron degeneracy. The core expands violently, dropping its temperature and slowing fusion to a stable rate. Convection zones plunge into the core, dredging up freshly minted carbon and mixing layers. Over minutes, the core reconfigures. It expands by a factor of 2, its density plummets, and a self-regulating helium-burning core establishes itself. This interior drama drives a secondary response in the overlying hydrogen shell. The luminosity of the hydrogen burning dips, causing the star's envelope to adjust. Over weeks to months, the red giant shrinks and settles onto the horizontal branch of the Hertzsprung Russell diagram, burning helium steadily in its core. Though the flash itself is hidden beneath thousands of kilometers of stellar material, its signature appears in the star's later evolution. Its luminosity drops by a few tens of percent. Its radius contracts by up to half. Surface temperature climbs from 500 K to around 0 K. Observers watching clusters of red giants see a clumping of stars at the horizontal branch stars that have undergone this violent rebirth. Spectroscopy reveals enhanced surface abundances of carbon and oxygen, fingerprints of the core mixing dredged upward. Though the helium flash remains invisible directly, its consequences sculpt stellar populations and anchor stellar evolution theory. With the flash behind it, the star enters a stable phase, fusing helium into carbon and oxygen for tens to hundreds of millions of years. Its life path now diverges from low-mass red giants that never reach the degenerate threshold. Ultimately, when helium is exhausted, the star will ascend the asymptotic giant branch, lose its envelope, and leave behind a white dwarf, the ember of a once explosive heart. But the great helium flash, that sudden burst of fusion under degenerate pressure, remains one of stellar astrophysics' most dramatic episodes. An event where quantum mechanics, nuclear physics, and gravity conspired in seconds to reshape a star's destiny. Both tail zone of two compact stars entwined in X-ray and gravitational duet, the other of a red giant's hidden core, erupting in runaway fusion span 15 minutes of cosmic drama, exploring extremes of density, energy, and time. Together, they illuminate how the universe's grandest transformations can play out in fireworks and whispers, in orbits and flashes, across the tapestry of space and time.